Welcome back, my dear friends. A very good morning, good afternoon and good evening to all of you. And so, as you know, this is the lecture or NPTEL MOOC series where the course title is Multi-Criteria Decision Making. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. This is the 36th lecture out of this 60 lecture series, and 60 lectures means spread over 12 weeks. And each week, as you know, there are 5 lectures, each lecture being for half an hour. And as you know, after each lecture of 5, that is each week you have assignments. So, there will be 12 assignments. These are already known to you, but I am just repeating. So, there will be 12 assignments and at the end there would be one final semester examination. The broader set of points, broader set of ideas, broader set of philosophies which we are discussing for a long time, for it is going on for quite a few weeks. The main points are related to multi-criteria decision making, multi-objective decision making, which we are still continuing discussing. Then we will go into multi-attribute decision making and multi-attribute utility theory and draw conclusions from multi-attribute utility theory, which I said it would be a little bit theoretical, and go into discussing the other so called qualitative methods of ranking. The examples which we were discussing in the last lecture was related to linear programming for MCDM, and then as I said, we will also go into the non-linear programming. Hopefully, we will be able to start this problem for non-linear programming. Now, where we closed the last day was this slide, where the top row had different coloring schemes of x1, x2, x3 given in red, violet, blue, and the next 3 column heading were f1 double star, f2, f3, f1, f2 double star, f3 and f1, f2, f3 double star, and the coloring scheme of red, violet, blue is clear to you. The values which you are seeing in this table are corresponding to the fact that you get a combination of f1, f2, f3. I am not reading this double star values, which should be obvious because these are the slides we are discussing. And if I add up the sum, what I am trying to optimize, based on that we obtained the different type of Pareto points. Now, a question would come which I will answer later on. So, let me do the other methodology of trying to do the multi-objective problem, and I will solve the same problem, this one which you see, considering the idea that how the ideas of if the weights come into the function, like if I give weights of 1/3, 1/3, 1/3 to f1, f2, f3, then that is fine, because I will be adding them and dividing by 3. So, in that case, for the multi-objective case, for these 3, when I add up the functional values and divide by 3, do not change. But if we give different weights like 80%, 10%, 10% for the first function, second function, third function, then the values would change obviously, because in the case if I put 80, 10, 10, that is 0.8, 0.1, 0.1. So, the value, if I consider the yellow marked cells only, it will be 39 multiplied by, this is the multiplication sign is of 0.8. No, I will do it the other way. Other way means a different. So, I will use the red color, because that is f1 double star being maximized. So, it will be easy for us to make the differentiation using the coloring scheme. So, the first part, this one. So, this will be 39 into 0.8, because we are putting 80% onto the first function, plus 18 into 0.1, because we are putting 10% function 2, and 18 into 0.1 because that is the weight we are putting for the third function. Now, if I follow the same scheme 80, 10, 10, 80%, 10%, 10%, then here it is 18 into 0.8 plus 39 into 0.1 plus 18 into 0.1. The value on the red shown and value on the violet, they will not be same, because we are putting different weights. Similarly, if I consider the blue one here, so this one would have 18 into 0.1 plus 18 into 0.1 plus 39 into 0.1. Luckily, the violet and the blue one are same, but it is not guaranteed, depending on the outcome we will have different answer. So, I want to show you an example later on after we discuss the second one, that how we can formulate another simple objective function which will be not dependent. It can be an example which would not be dependent on the weights we are giving. But having said of the weights, let us consider the other methodology of trying to solve the multi-criteria problem. Before we move to the weighted concept, let us consider the 3D plots of F1, F2, F3. So, as these programmings were all done in R, so all the graphs and the results which you see for so here we have variable 1, variable 2, variable 3. Technically, variable 1 is on the floor where I am standing. Variable 2 is going from my side towards the camera, that is towards the students, and variable 3 is coming from the ground going vertical up, which is a 3-dimensional one, and they are orthogonal to each other. So, the points which you see, I have not been able to plot the plane, but I will try to analyze that later on, that you will be able to get the Pareto points as we just discussed. That was given the value wise, how you can visualize pictorially, that will come later on. Having said that, let us go in trying to utilize the concept of not transferring the objectives into the constraint, but giving weights. So, the weights we consider for function 1, function 2, function 3 are, this is function 1, this is, so the weights is lambda 1, this is function 2, weight is lambda 2, this is function 3, weight is lambda 3. And if you see the constraints, this is the same problem which you had considered, these are the same constraints, 5 in number, and important point which we all know, all the weights should be between 0 and 1 and the sum of the weights is 1. So, you can basically do a permutation combination trying to find out what are the weights based on that. We will follow that scheme later on also. Now, and this is a linear programming, and we can solve the the integer part also of this. If you remember one problem we have solved, the same problem which was in 2-dimensional case, we took linear programming and integer programming. By the way, for this problem which you are solving giving the weights, we will solve it using the linear programming. That means, the variables are continuous, and we can also solve the problem considering the variables are integer. Now, the question which you all would ask, the problem for which we have been discussing in the last class, could that has been solved in the using the variables integer? Yes, they could have been solved. I did not do it, but I am sure you got the gist and the essence of the discussion. Now, I take different combinations and the combinations I have enumerated all of them for simplicity, for ease of understanding, for getting a better viewpoint, whatever you can say. So, I took the values of lambda 1, lambda 2, lambda 3. Why I am putting colors? Because they were corresponding to red, violet, blue for F1, F2, F3. And if we add up column 1, 2, 3, which are marked for lambda 1, lambda 2, lambda 3, the sum are all 1, 0.1, 0.1, 0.8, 1. And you go 0.1, 0.2, 0.7, 0.1, 0.3, 0.6, 0.1, 0.4, 0.5, 0.1, 0.5, 0.4, 0.1, 0.6, 0.3, 0.1, 0.7, 0.2, 0.1, 0.8, 0.1. So, all the values here add up to 1, remember that. Now, as I solve them, I get the following values, and the objective function is as it was the weighted values, the weighted values being lambda 1 into F1 plus lambda 2, this would be lambda 2 into F2, and final being lambda 3 into F3. And the values which I get, I will mark. These are the decision variables. So, this is x1, x2, x3, and the objective function, which is convex combination of F1, F2, F3 is given. Now, immediately you may jump to the conclusion, and that may be an interesting snapshot here. If you consider these 2 points, 2 sets of points. So, let me use the, if you use this one 32 here, 32 here, objective functions are same, but interestingly the decision variables are 0, 0, 20 and 0, 20, 0, which can be considered as a Pareto points for the same objective function value. Now, if we look, do we have any other sets of Pareto points? For the case, if I use the green color, this is 26, 26 objective function, and the Pareto points are 0, 0, 20 and 0, 20, 0. Now, if I consider these two and these two, the points are same, but the objective function values are different. Why? Because the weights are different, that should be remembered. Continuing the discussion again, lambda 1 F1, this is lambda 2 F2, last is lambda 3 F3, and the values of lambda 1 first column, lambda 2 second column, lambda 3 third column are given here for different values of lambdas. Sum is 1, remember. So, it basically the first column are all values of lambda 1, which is 0.2, and the second and third column are lambda 2, lambda 3, and based on that, when we solve the linear programming problem, x1, x2, x3 are given here, and the objective function values are given. So, if I consider again for simplicity 20, 20 the objective function values, and the Pareto points are 0, 0, 20, 10, 10, 10. Similarly, if I consider this 30 here, which you already considered earlier. So, it was 0, 20, 0, and the 30 value here was basically 0, 0, 20. So, again you will have the same decision variable outputs, objective functions are different because based on the lambda values we have. So, these are lambda 1 f 1, again I will highlight that this is, so lambda with the suffix 2, lambda 2 f 2, lambda 3 f 3. These are lambda 1, lambda 2, lambda 3, sum is 1. These are the decision variables. And obviously, for the case for example, these are all 20. Decision variables are x 1, x 2, x 3 are all 10, but the combinations which we are taking for lambda 1, lambda 2, lambda 3 are different here. What they are? They are for the same output, which is the decision variables as well as the objective function. They are as follows. Here 30%, 20%, 50%, 30%, 30%, 40%, 30%, 40%, 30% corresponding to f 1, f 2, f 3. Similarly, lambda 1 here, lambda 2 here, lambda 3 here, sum is 1, remember this is lambda 1 f 1, this is lambda 2 f 2, this is lambda 3 f 3, and interestingly, watch this 20, 20, 20 decision variables. If you see here, these are the whole set of decision variables, but for a value output objective function 20, the values are 20, 0, 0, 10, 10, 10 and 0, 20, 0. Now, if you go back here for 20, we already have 10, 10, 10. So, apart from 10, 10, 10, we have 20, 0, 0 and 0, 20, 0. That means, they can be considered as the set of Pareto points corresponding to an output of 20, but one should remember the lambda values are also significant here. The lambda values were 40, 20, 40, 40, 30, 30, 40, 40, 20 corresponding to the weightages, and they are in percentage, weightages given to f 1, f 2, f 3. These are when lambda 1 is 0.5, I am enumerating all of them. Lambda 2 second column, lambda 3 third column, this is lambda 1 into f 1 plus lambda 2 into f 2 plus lambda 3 into f 3. Sum of all the lambdas is 1 as usual. The decision variables different combinations are given here. And if you see here, there are values of the objective function 26, 22, 20 and 24, but obviously, we have other such objective function outputs here also. 26 is here. So, one Pareto point is 0, 20, 0, another point is for 26 is 20, 0, 0. Here for 24, one Pareto point is 20, 0, 0, here one point is 0, 20, 0. For a value of 20, we have already seen that 10, 10, 10 was there, 20, 0, 0 was there, 0, 20, 0 is there, and finally, the value of 20 can be obtained with values of 0, 0, 20 also, depending on the combination. For a values of lambda 1 as 0.6, column 1, lambda 2, column 2, lambda 3, column 3. So, this is first part of the objective function. second part of the objective function, which is lambda 2 f2, third part of the objective function lambda 3 f3, and the sums of the lambdas is 1, as you can see, adding up the corresponding cell values for first, second, third column, and row wise you are adding. The values of decision variables are given here, and 28, 24, 22 is given here. You can just double check with 22 is there here, if you see, is 20, 0, 0, 22 here is 0, 20, 0. And if I want to see any other 22, let us see, there is a 22 here, is 20, 0, 0. So, any combination. So, here you have 22, 0, 20, 0, 0, 20. So, 22 can be obtained by all combinations of 20, 0, 0, 0, 20, 0, 0, 0, 20. But remember, the weights are changing, which is lambda 1, lambda 2, lambda 3. Second last table here is for lambda 1 0.7, lambda 2 as given as 0.1, 0.2, lambda 3 given, remember, sum add up to 1. This is lambda 1 into f1 plus lambda 2 into f2, lambda 3 into f3, and the decision variables are this 20, 0, 0, 20, 0, 0 for the objective function 30, 26. Finally, for lambda 1, lambda 2, lambda 3 given in column 1, 2, 3, and obviously the sum is 1. The objective function is lambda 1 into f1 plus lambda 2 into f2 plus lambda 3 into f3. Decision variables solved are 20, 0, 0, give a value of 32. So, I have enumerated all the combinations of lambdas in jumps of 0.1 and shown the decision variable values and the objective function values. Now, let us collect all the data. So, first we correct this one, this is lambda 1 plus f1, this is lambda 2 f2, lambda 3 f3, and for different values of lambda 1, lambda 2, lambda 3, we get the value of 32 as the objective function, which is shown in the last column, which is here, and the combinations of the decision variables are as given here 0, 0, 20, 0, 20, 0, 20, 0, 0. So, if I for the time in only concentrate for the values of decision variables, which can be considered as a Pareto optimal points, because we get a value of 32 for all the 3 cases of the objective function, then the Pareto optimal points are 0, 0, 20, again I am repeating 0, 0, 20, 0, 20, 0, 20, 0, 0. Now, if I consider objective function of 30, the Pareto points are 0, 0, 20, 0, 20, 0, 20, 0, 0. Now, the question would immediately come up that we are getting the same Pareto points. That is because we are taking the values of lambdas differently. So, I will draw it again for different values of lambda, lambda 1, lambda 2, lambda 3. So, this is lambda 1 into f 1, lambda 2 into f 2, lambda 3 into f 3. We get 28 in one case for some concepts combinations of lambda, 26 in another case for other different combinations of lambda, and 24 for another third case for other third sets of combinations of lambda. The values which are given here x1, x2, x3, correspondingly the decision variables are is 20, 0, 0, 0, 20, 0, 0, 0, 20. That should be looked on from the point of view as the Pareto points. Let us for the time being ignore the case of the lambda values. Finally, lambda 1 in plus f1 into f1, lambda 2 into f2, lambda 3 into f3. The values are 22 objective function and 20 objective function, and the decision variables continue to be 0, 20, 0, 0, 0, 20, 0, 0, 0, 20. Now, the reason why I am going to draw it for the last one, which is this a little bit orange and yellow and little blackish one color here, is because it has got 4 points and it will be easy for me to analyze. So, let me draw this set points, and I am ignoring the concept that the lambdas are there, but I am only concentrating on the objective function value and the Pareto points. So, I will basically do that. I will create a, now here comes the, so I will only consider the last 4 where the objective function is 20, and the points I will repeat are 20, 0, 0, the third one, then 0, 20, 0, the second one, 0, 0, 20, the first one, and last one being 10, 10, 10. If I draw the surface, consider this is x1. So, these are all orthogonal. One is on the floor, another is vertical up, and another the wall going towards you. So, based on that I draw. So, this mark is x1, this I mark as x2, this I mark as x3. What are the points? 20, 0, 0. So, let us take 20, 0, 0. I will use same color, they would not be much of a difference. So, same color. So, if I mark 5, 10, 15, 20, 5, 10, 15, 20, 5, 10, 15, 20. So, if I consider this is 20, 0, 0. So, this is 20, 0, 0. This point is 0, 0, 20, because x3 is value and this value is 0, 20, 0. So, if I draw it, this is the slanted triangle which I have. So, all the points, and interestingly, if I consider the point 10, 10, 10, so I will go 10 on to the right x1, then I come forward for x2, and then I go up. So, it will be some point in the 3 dimension which is 10, 10, 10. So, it will come out 10, it comes out, 10, it goes up. So, this is the 10 would be the point. So, it will be somewhere here, even though it actually is an equilateral triangle, it should be the midpoint, but I have tried my level for all the set of points would be the Pareto surface, where the objective function is, as I calculated, was given as 20. So, with this we will end this class and continue discussing more about Pareto points, and all were linear programming, and the same analysis can be done for the integer programming. We will basically come to the quadratic programming and nonlinear programming later on. So, thank you very much for your attention. Have a nice day.